The James Webb Space Telescope has found evidence of human activity far from Earth, bringing us closer to answering the age-old question of our solitude in the universe. The research for extraterrestrial life has been a constant throughout human civilizations, generating thousands of literary works and theories on the subject. Our fascination with our place in the universe and the possibility of not being alone seems to be ingrained in us, driving us to seek companionship, even if it's of extraterrestrial origin. We're getting closer and closer to finding answers to questions we really want. But are these answers really what we seek? Or is there something deeper at play? In 2021, the James Webb Space Telescope posed a hypothetical question about the future capabilities of our technology. Could our telescope detect artificial light on another planet, such as Proxima B? This exoplanet, the closest to Earth, lies in the habitable zone of our nearest neighboring star, Proxima Centauri, about 4.25 light-years away. Proxima B was believed to be locked in synchronous rotation, similar to the Moon with Earth, with one side always facing its star. The possibility was raised that a technological civilization on Proxima B could transfer the heat and electricity from the day side to the night side using probalictic cells that generated electricity from sunlight. Subsequently, a paper with Manas V. Lingam as one of the researchers showed that significant coverage of the day side with solar panels could be detected by future telescopes. Given that the James Webb Space Telescope represents a more advanced technological advance, now in 2024, there is a possibility that will allow us to expand our research for possible artificial lights on habitable exoplanets such as Proxima B. Thanks to its increased sensitivity and range of capability, the JWST may have discovered the light we've been looking for, which could propel humanity towards another great leap in its evolution. But before we dive into the implication of this discovery, it is crucial to understand how this feat was possible. The James Webb Space Telescope mission explores the mysteries of Proxima Centauri B. Throughout history, humankind has sought answers to understand the fundamental questions about the universe, our existence, and destiny. These common but extremely difficult questions have been driven humanity's curiosity for as long as we have been conscious. In the current era of exponential technological advances, the question arises as to whether we are any closer to finding answers. While a philosopher might argue that we are still at an early age in our understanding of the universe and ourselves, and astronomers would be excited to share the latest discovery about the cosmos, using the technological tools at his or her disposal. Although these advances often go unnoticed by the general public, they truly represent milestones in human evolution. Now, with the world literally at our fingertips, it is time to move forward and explore the universe in ways never before imagined. One of the ways of exploration is through technology, such as the James Webb Space Telescope. This instrument, heir to the legacy of human space exploration, is destined to answer fundamental questions about our place in the cosmos. It has already begun to shed light on the possibility of life beyond our solar system, as evidenced by the recent discovery of possible lights on a planet light years away. Proxima B, also known as Proxima Centauri B, is a superterrestrial exoplanet orbiting an M-type star. These planets, more massive than Earth but lighter than ice giants like Neptune or Uranus, are a unique class in the universe. Although much remains to be discovered and understood about Proxima B, this breakthrough represents a significant step forward in our quest to better understand our place in the cosmos. The first possible evidence of an exoplanet dates back to 1917, although at that time it barely captured the attention and recognition of the scientific community. However, it was in 1992 that the first detection of an exoplanet was confirmed, astounding scientists. Since then, many other exoplanets have been confirmed, with another notable example in 2003. By April 1st, 2024, a total of 5,653 exoplanets have been confirmed, in 4,161 planetary systems, of which 196 have been more than one planet. These marvelous discoveries are mostly associated with M-type stars, also known as red dwarfs. Red dwarfs are the smallest stars on the main sequence that are considerably more common in the Milky Way than other stars. However, due to their low luminosity, observing them is not as easy as with other stars. Red dwarfs have different classifications and names according to their temperature and sizes, often designated as M dwarfs. These stars, with a temperature of about 3,900 Kelvin, have specific characteristics that distinguishes them. As Proxima B, its mass is estimated to be about 1.07 times that of Earth. Remarkably, it completes an orbit around its star in only 11.2 days, compared to our Earth year of 365.25 days. This gives us an estimate of the size of the star orbiting Proxima B. The star's luminosity is surprisingly low across the electromagnetic spectrum, at only 0.16% of the sun's luminosity. Moreover, in the visible spectrum, its luminosity appears even dimmer, emitting only about 0.056% of the sun's luminosity. More than 85% of the energy it emits is in the form of infrared radiation, and it orbits at a distance of about 0.4856 astronomical units from its star. The discovery of Proxima B was announced in 2016, which raises the question of why this particular exoplanet has generated so much interest. One of the reasons is that Proxima B is the closest known star to our Sun, albeit at a distance of 4.2 light-years, which, while larger to us, is relatively short on a cosmic scale. It is part of the triple star system known as Alpha Centauri, and despite its low luminosity, remains an object of great interest to astronomers. The Proxima Centauri system stands out as one of the constellations visible in the night sky, ranking behind only two others, known as Sirius and Procyon. However, the most intriguing thing about Proxima Centauri B is its potentially habitable position within the habitable zone of its star. Possibilities they suggest are limitless, which has led astronomers to embark on an expedition to explore the depths of this stellar potential. This is where the James Webb Space Telescope comes into play. The four main goals of the JWST include searching for light from the first stars and galaxies that formed after the Big Bang, studying the formation and evolution of galaxies, understanding the formation of stars and planets, and investigating planetary systems and the origins of life. As JWS continues its exploration of exoplanets such as Proxima B, we move ever closer to achieving these goals. The search for extraterrestrial life is a particular area of interest in space exploration. The Search for Extraterrestrial Intelligence (SETI) project stems from the curious nature of humanity, exploring all that moves and all that does not move. SETI imagines a kind of cosmic treasure hunt, where instead of gold, we are in search of electromagnetic signals that could be whispers of civilizations beyond our wildest imaginations. A surprising discovery made by the James Webb Space Telescope has captured the attention of the scientific world: the detection of urban light signals in space, located at a distance of 7 billion kilometers from Earth. This unexpected finding has sparkled great interest in the possibility of extraterrestrial life. By focusing on Proxima Centauri B, the closest exoplanet to Earth, the telescope revealed the presence of unusual bright lights emanating from its surface. What could be the cause of these unusual lights on Proxima Centauri B? Could they indicate the existence of life beyond our own planet? For years, mankind has longed and searched for signs of life beyond our own solar system. Any hint suggesting the possibility of this fantasy has been greeted with great enthusiasm. Recently, the scientific community was stunned when the James Webb Space Telescope captured compelling evidence for the existence of life forms in space. While exploring the cosmos and transmitting critical data back to Earth, The telescope observed unique urban lights coming from the exoplanet Proxima Centauri B. These lights, as their name suggests, are the first to be seen in space. These lights, as the name implies, appear to illuminate a distant city. The idea of the existence of an alien civilization in this star system has perplexed scientists, filling them with wonder. Each is baffled by the possibility that this is the discovery they have been all waiting for. If confirmed, it would mean that there are intelligent life forms that have developed societies beyond our comprehension in outer space, and we are just beginning to discover it. Observing these urban lights from a distance of 7 billion kilometers, NASA engineers wonder how long they have been glowing in space, waiting for mankind to develop the technology to detect them. David Kipping, an astronomer at Columbia University, characterizes the exoplanet Proxima B, where the urban lights have been sighted, as a celestial body with peculiar heating patterns that differ from those observed on other planets. While conventional rocky planets tend to absorb sunlight and emit infrared radiation, this exoplanet exhibits a markedly different infrared nature from its host star, Proxima Centauri. This peculiarity has allowed careful observation by the James Webb Space Telescope, the JWST, since this instrument is highly sensitive to infrared wavelengths. The thermal signature of Proxima B will play a crucial role in investigating the universal secrets of its atmosphere, taking advantage of the JWST state-of-the-art infrared imaging capabilities. Scientists plan to use this telescope to unravel the planet's atmospheric mysteries, as well as to assess its potential habitability. The JWST, with its exceptional infrared sensitivity, is equipped to probe the nights on Proxima Centauri B because it can pick up even the faintest light signals in the cosmic darkness. It becomes the ideal tool for verifying the existence of possible city lights in the night of Proxima B. JWST's ability to detect artificial illumination in the cosmos is due to its ability to operate within an extremely narrow frequency band, 1,000 times narrower than starlight. Proxima B exhibits an interesting relationship between its stellar features and its surface interactions, with its daytime side adorned with solar panels that harness the energy of its host star, while its night side time experiences cold temperatures. The temperature variation on Proxima B, as determined by its atmospheric composition, is an intriguing topic for astronomers, and the JWST can effectively probe the planet's thermal emissions to provide crucial data on its atmospheric properties. In addition, JWST's orbit around Earth aligns with the orbit of Proxima B, allowing full observations of its diurnal and nocturnal cycles in 11.2 Earth days. The next step will be to assess the atmospheric chemistry of Proxima B to determine its potential to support life, focusing on the presence of gases such as oxygen, water, vapor, and methane as key indicators of habitability. If elements such as oxygen, water vapor, and methane are detected in the planet's atmosphere, it could mean that it's capable of supporting habitable conditions. However, this process is extremely challenging, as it involves the meticulous capture and analysis of the light rays passing through the planet's atmosphere. Although the James Webb Space Telescope, the JWST, has great capabilities for characterizing planetary atmospheres, its focus is primarily on analyzing variations in the concentration of water vapor, carbon dioxide, and methane. Detecting oxygen, a crucial indicator of life, is more limited for the JWST. Despite these limitations, the telescope still looks for other elements such as ozone, which may also provide clues to the planet's habitability. It is important to keep in mind that the JWST cannot explore all potential habitable worlds, as it has limited capabilities and can only observe some of the exoplanets closest to Earth. Therefore, astronomers are turning to ground-based observatories such as the Extremely Large Telescope, the LELT, which is expected to become operational in 2028 and allow for a deeper investigation of the atmospheric structure of distant exoplanets. Scientists eagerly anticipate the development of future space telescopes that will expand our understanding of exoplanetary exploration. Although the JWST has limitations, so to say, it remains a crucial tool for unraveling the mysteries of distant exoplanets. However, future space telescopes will aim to reduce the glare from host stars in order to better study light reflections from the exoplanets themselves. This presents additional challenges, as scientists must distinguish between gases produced by life and those generated by geological processes on the planet. Despite these challenges, scientific advances continue to move forward, and the Webb Telescope represents a step forward in our understanding of exoplanets and the universe in general. Despite an exhaustive search in all corners of space, scientists have not yet succeeded in finding any planet capable of supporting life. Throughout decades of research and search of signs of life in the cosmos, the question still remains: are we alone in the universe? James' achievements on the Webb have exceeded our expectations, consisting of a 6.5-meter mirror, a sun shield the size of a tennis court, and a complex array of instruments cooled to temperatures near absolute zero. The telescope observes the sky in infrared radiation, revealing details of the universe just after its birth 13.8 billion years ago. It captures images of stars born in clouds of dust and collects faint light from the deepest of the universe, exploring its darkest corners. The infrared instruments of the space-time network are also useful for studying strange and bizarre worlds. In particular, James Webb has focused on Proxima B, capturing the sharpest image of our closest known neighboring exoplanet. What's fascinating is that what it has revealed goes beyond our expectations. In January 2024, we have reached a remarkable milestone in our understanding of the universe. For millennia, humans have observed the sky, wondering about points of light in apparent infinity. Just 3 decades ago, we began to discover planets orbiting other stars through a variety of methods. Now, 55 confirmed exoplanets and 10,000 additional candidates. We are in a new era of astronomy, exploring fascinating and diverse worlds beyond our own solar system. Planet formation exhibits remarkable diversity, determined by a number of factors including the chemical composition, geological activity, and atmospheres. When findings point to the presence of worlds with chemical elements, even superficially related to life, the discoveries are significant, providing answers to some of our questions about the cosmos. However, deeper questions remain. In this context, the mission of the James Webb Space Telescope is focused on exploring the atmospheres of exoplanets for signs of life in other corners of the universe. Although James Webb is an infrared telescope, which raises the question of its suitability for studying exoplanets, it will use the transit method for this purpose. This method involves observing the light from a star as a transiting planet passes between the star and us. Collaboration with ground-based telescopes will complement this research by allowing measurements of the mass of planets using the radio velocity technique, which detects the slight wobble induced by a planet's gravitational tug. In addition, James Webb will perform spectroscopy of planetary atmospheres and carry coronagraphs to obtain direct images of nearby exoplanets. Although these images may appear to be simple points of light, their detailed analysis will reveal valuable information, such as color variations that may indicate seasonal or rotational differences in vegetation. Spectroscopy, which involves measuring the intensity of light at different wavelengths, is fundamental to unraveling the atmospheric compositions of exoplanets. When a planet transits in front of a star, starlight passes through its atmosphere, and the elements in compounds present in the atmosphere absorb light at characteristic wavelengths. This absorption is reflected in the observed spectrum, making it possible to identify the presence of elements such as sodium, methane, or water. An infrared telescope is essential for characterizing the atmospheres of these exoplanets because many of the gases relevant to the search for life, such as water and carbon dioxide, emit and absorb light in the infrared range. In addition, this wavelength provides valuable information about the temperature and chemical composition of the atmospheres, which contributes significantly to our understanding of the habitability of these distant worlds. Observation in the infrared spectrum offers the advantage that the molecules present in the atmospheres of exoplanets exhibit a wide range of spectral characteristics. The ultimate goal is to discover a planet with an Earth-like atmosphere, and in this effort, to find an Earth 2.0, the James Webb Telescope has turned its attention to Proxima B. This enigmatic exoplanet, located light years away, is the closest known neighbor. Proxima Centauri B is a super-Earth orbiting an M-type star with a mass approximately 1.27 times that of Earth and an orbital period of 11.2 days. This planet lies at a distance of about 0.085 astronomical units from its star within the habitable zone. However, the extreme intense ultraviolet radiation it receives from its star poses challenges to habitability, as this radiation can erode the atmosphere and compromise the presence of elements essential for life, such as oxygen and nitrogen. The habitability of a planet depends not only on its location in the habitable zone, but also on the ability of its atmosphere to maintain conditions suitable for life, such as climate regulation, radiation protection, and preservation of necessary chemical components. In addition to Proxima B, James Webb is also interested in other exoplanets, such as WASP 107b and the wandering worlds of the Orion Nebula, which challenge our conventional conceptions of planetary formation. These recent discoveries have opened up new questions about the formation and diversity of objects in the universe, challenging our existing theories and stimulating continued explorations of the cosmos. We were on the lookout for astronomical tiny objects, and we have found them, even as small as half of mass of Jupiter, floating freely in space, unbound to any star. Physics tells us that objects of such a small scale should not exist, but we seem to have defied those laws. These bodies, which are technically not planets, have been dubbed Jupiter mass binary objects because several of those identified come in pairs. Although these two jumbos are 2 of 1 million years old, which is very young in astronomical terms, their first surface temperatures reaching a scorching 1,000 degrees Celsius, although they will eventually cool. Although these objects may exhibit interesting atmospheric features, such as the presence of steam and methane, they are not considered capable of harboring extraterrestrial life, as their surfaces could not sustain liquid water, even during their brief period of moderate temperature. These observations have focused on the Orion Nebula, a region of massive star formation located 1,344 light-years away from Earth. This nebula, visible to the naked eye as a fuzzy star in the sword of the constellation Orion, is a celestial spectacle filled with clouds of dust and gas, where explosions and gravitational collapses occurred and give rise to formation of stars and other celestial objects. The most recent findings have puzzled astronomers, especially the presence of numerous pairs of Jupiter-sized objects. The question of how these objects can be flown out of a star to orbit in chaotic interactions and then rejoined remains an enigma. Even experts like Professor Matthew Bates, head of astrophysicists at the University of Exeter, acknowledged that they have no definitive answer to this anomaly. It seems that our current theories are not sufficient to fully explain these new findings. There is an unknown mechanism that is shaping these objects, something we have not yet considered. This type of discovery is quite unusual and challenges us in our understanding of star formation, an area we thought we understood quite well. It is a surprising result from which we can learn more about. Let us know what you think in the comments box. If you liked the video, remember to like it, share it so it reaches more people, and subscribe so you don't miss out on more content like this.